Alright everybody, here's a couple of pointers. This is homework problem number 2. I think before you just start chugging along on this, you should think about what are you expecting to see as the answer. So, if you remember, I hat and j hat are the right pointing and up pointing vectors. So really this is the same thing as if I had written a vector that was sine 2t as the x component and negative secant squared t as the y component. So I'm integrating this. Are we expecting this to be a vector equation as a function of time? Are we expecting it to be a constant vector? Are we expecting it to be a number? So you can kind of think your way through this by sort of working backwards. So if I have just some random vector equation like t squared 2t, and I take the derivative of this, I should get another vector equation. You know that much. So if I start with a vector equation and I take an integral, you should get another vector equation out. But that's an indefinite integral. So what happens if you take the indefinite integral and make it into a definite integral? That would be like evaluating this antiderivative at these two times. So if you think about it, it's like saying, what is this antiderivative vector at time 1? What is the antiderivative vector at time 2? And sort of what's the difference between those two vectors? So that's what we're really going to be doing here. All right, so let's do it in 2 steps. So first, let's just figure out what happens when we integrate these two parts separately. So this is going to give us negative 1/2 cosine 2t. But remember, this is still just the x component, so I'll keep the I hat there. And then the y component, this should just be tangent t, and I'll keep the j hat there because that's the y component. And I'm going to be evaluating that from time is pi over 6 to time is pi over 3. All right. Maybe let's stop writing it with I hat, j hat, and let's start writing using the triangle bracket notation for x component, y component. So if I evaluate this, I'm going to have negative 1/2 cosine 2 pi over 3. Well, let's keep the I hat, j hat. Minus tangent pi over 3 j hat. So I've got all that minus the same thing evaluated, so minus 1/2 cosine 2 pi over 6 I hat minus tangent pi over 6 j hat. All right, well, remember, the I hat ones are the x components and the j hat ones are the y components, so you can't just combine all of these values together. I'm just going to call this value A, this value B, this value C, this value D. So what we've got is, if you combine the two x components together, we've got A minus C, and then we've got B, let's make the B include the negative sign, B minus D, j hat. So A, B, C, D, these are all just numbers. So this is a vector for sure, but it's not a vector equation that's a function of time. It's just a constant vector. And that's sort of what you would imagine it to come out with if you think about what we talked about initially up here. Okay, good luck. A few quick pointers for 4 and 5. So if I'm asking for the angle between 5, negative 4, so kind of this vector, and negative 7, negative 1, so kind of this vector, that's this angle here. If you remember dot products, the dot product of two different vectors is the product of their magnitudes times the cosine of the angle between them. So and that's also calculated as multiplying the x components, multiplying the y components, and adding those two things together. So that should give you an equation where the only unknown is cosine theta. And so then you can solve for it, and that's a good approach to number 4. Number 5 is kind of the same idea, only now instead of two constant vectors, and we're using the dot product to find the angle between them, now we've got two vectors that are changing over time. So for problem 5, we're imagining, let's see, the vector P1 is 2t as the x component and 3 as the y component. So at time 0, the vector looks like this, but as time goes on, it kind of moves out this way. The y component is always 3, but the x component is moving this way. So that's P1. And then for the vector P2, we've got 5t and 1. So in this case, the y component is always 1, but as time increases, the x component is increasing, but at a much faster rate than vector 1. So we've got these sort of two vectors, and if you imagine them over time, they're each kind of shooting off this direction. So the question is, as they're moving, eventually this angle between them is going to kind of open up because the bottom vector is moving off to the right way faster than this vector is. So the question is, when will that angle exceed 30 degrees? So we can set this up in the same way. We know that P1 dot product P2, the way you're going to calculate it is multiply x, multiply y, and add together. So that's going to give us 10t squared as the product of the x's, plus 3 as the product of the y's. That's equal to the magnitude of P1 times the magnitude of P2 times cosine theta. Okay, well you can work out equations for those magnitudes. That's going to give you a kind of a messy expression in terms of t. So then all you need to do is you want to solve for when the angle exceeds 30 degrees. So you want to solve for the condition when that's 30 degrees. If you plug that in, now you'll just have a big messy equation in terms of time, which you can totally feel free to solve numerically if that's what you're into. Okay, let's look as a last one at number 6. Here I have graph number 6, so let's assume maybe unrealistically that the baseball man for some reason has hit the baseball from the ground. So I'm going to place my coordinate axes here. And it's going to fly in a parabolic arc, and it's just barely going to clear this fence that's 9 feet tall and 390 feet from where the dude hit it. So the question is, we don't know how fast the ball was traveling initially. That's a mystery, but I'm going to call that S. So the magnitude of that vector is S. What we do know is that that's 30 degrees, and we also know that at a particular time, at a particular unknown time, the ball was at exactly this point at 390 and 9. Okay, so this is the usual thing where you want to write down all the things that you know, write down what you want to know, and then try and bring the two together somehow. So I had said in class that a good idea is just go ahead and write down the acceleration, velocity, and position vectors just kind of immediately, because that's going to give you a lot of equations where you can plug things in and solve for other things. So I think it's a good idea just to slap that out there. So the acceleration, because this problem's all in terms of feet, let's write the acceleration vector in the units of feet per second squared. So it should be a constant vector downwards. Just like we did in class, you can integrate this vector here to get your velocity vector. The only difference is we don't actually know exactly what the velocity vector is because we don't know what that initial speed was. Here's what we do know, though. The initial velocity vector has got to be whatever that speed is times the cosine of that initial angle as the x component, and the speed times the sine of the initial angle as the y component. So we can still write the vector, it's just got this variable in it. So that's s cosine 30, and then s times sine 30. So when you integrate the acceleration vector, you'll get the velocity vector, and you'll just need to put these two parts in as the initial velocity. And then you integrate again to get your position vector. Once you've got all of those, just try and write down what else you know is true. We know that at a particular time, let's pretend that we've got these equations. So the position vector, we've got some equation that's a function of time for x and some that's a function of time for y. So we know that at some mystery time, x of t should be 390, and y of t should be 9 feet. Well, okay, if we rate these equations out, I've got two equations, and each of these equations is going to have two variables in it, and that's all you need to solve. I think that's enough hinting for the moment. And I think that's all the problems I want to talk about right now. So, tomorrow in class, I have instructed the sub to have you check extensively with your neighbors and to make corrections in a different color pen than what you did on the homework. I'm not there, but it's super important that everybody in your group understands how to do each of these problems. I will see you all on Monday. I hope you have good weekends.